All right, I think we'll get started. So today we're going to leave hydrogen and go on to the rest of the periodic table. So we'll be talking about so-called multi-electron atoms. In particular, we'll talk about the Pauli Exclusion Principle, along with a couple of other rules that will be important in developing what's called the electron configuration for these elements, which is really a shorthand notation for the ground state wave function for these multi-electron atoms. Now, if we go back to just a solar system model, just to get our bearings here, we of course know that we don't use a classical picture, we use quantum mechanics, as we've been working on the past few days. But just to get us set in terms of what the energies involved are, when we look at hydrogen, we have just a single electron and a single positively charged nucleus. And in this case, we have only one source of interaction here, electrostatic attraction. Now, when we go to helium or any other multi-electron atom on the periodic table, we introduce another electron. And we still have the electron nucleus, which is identical to this, with the slight exception that now there's multiple protons here as well. So for helium, there'd be two here. And we have this. So effectively, we have two electron nuclear interactions. But we also have this third so-called electron interaction. And it turns out this causes really big problems. So for hydrogen, we are able to do the quantum mechanics of hydrogen, solve the equations of quantum mechanics to get the wave functions, which we call atomic orbitals, get the rules for the energy levels, and all the things that we've been doing with hydrogen lately. As soon as we have an electron-electron interaction, so as soon as we move from hydrogen just to helium, the next element over, we cannot solve this problem. We don't have an analytic method for solving the equations of quantum mechanics that involve an electron-electron interaction. Now, there's a couple of things we can do that work quite well for helium and other at least low multi-electron atoms. And one of this is a category of approximation methods. So here we still want to work with pencil and paper, do quantum mechanics. We can't get a full solution or exact solution, but we can employ an approximation method that does quite well and matches experiments very, very well. We can do a numerical calculation. And so if you mount the equations of quantum mechanics onto a computer and you have enough computing power, you can calculate as accurately as you would like. So we can get very accurate calculations for multi-electron atoms to compare with experiment. A third approach, which might seem a little bit crazy, and that is to ignore the problem and hope it goes away. And in some sense, it does. So when we ignore the electron-electron interaction, we certainly cannot expect to be quantitatively correct, because this interaction is about the same strength as the attractive interactions between the electron and the nucleus. So it isn't small, so we can't ignore it for that reason. In a sense, we just ignore it, try it, and see what happens. So it turns out that we will still get a very, very good qualitative picture of other atoms. And in fact, professional organic chemists, professional inorganic chemists use this all the time. And what we get is something called a product state of hydrogen. And so how do we think about that? Well, we say, okay, if we ignore this, then really we just have two hydrogens in one. And although we'll get to this in later courses in this curriculum, one of the theorems in quantum mechanics states that if that's the case, if these are depending on like two independent hydrogen atoms, then the result of the quantum mechanical calculation will be the product of the two results for hydrogen. And so we already have those results. Those are the atomic orbitals. And there we go. Now, again, we can't expect this to be completely right. If we add some additional information that we know from either a more sophisticated look at the theory or from experiment, then we can get actually a very, very good description of the multi-electron atoms. And that involves three principles: the Pauli Exclusion Principle, the Aufbau Principle, and Hund's Rule. So we'll talk about all of those as we go. Now, as we look at hydrogen, we've done the energy levels for hydrogen, and we can see there's the 1s, the 2s, the 3s. These are all degenerate. Well, one of the consequences of the electron-electron interaction is to split the degeneracy here. So, for example, the 2p's are no longer degenerate with the 2s when we have more than one electron present. So that splits. So let's look at the multi-electron case. And we see here the 2s and the 2p have split, and they split such that the higher L value is slightly higher in energy. And so we go 2s and then up a little bit to the 2p. Well, this continues, and the 3s is split, the p's, 3d's split even higher, such that actually the 4s's are below the 3d's. So let's look at how we then describe multi-electron atoms. We'll start first with helium. So we employ what's called the Aufbau principle, or the build-up principle, and that is, however many electrons we have, we're going to start filling these electrons from the ground state up. So with helium, we have 2 electrons. We put the first one in any way we want. Okay? Now, the Aufbau principle says we should put the electron down here, and so maybe we write something like this. Okay? Well, now we have to employ a second principle, the Pauli Exclusion Principle. Now, the Pauli Exclusion Principle is actually a pretty advanced topic, but the consequences of the Pauli Exclusion Principle are what is taught to us as the Pauli Exclusion Principle in general chemistry settings. So if you look at the general chemistry book that you're working with, it will say the Pauli Exclusion Principle either states that no 2 electrons can have the same 5 quantum numbers, or it will say no 2 electrons can occupy the same state, including the spin space state. Now, technically, that's not the Pauli Exclusion Principle. The Pauli Exclusion Principle is talking about some symmetries of the wave function when you exchange electron 1 and electron 2, for example. But we don't need to get into that level. We just need to know what are the consequences. And the consequences are that no 2 electrons can be in the same state or share the same 5 quantum numbers. Those are equivalent statements. So let's look at this. This is a 1s, m equals 0, spin up. So it's a 1s, 0, 1/2, 1/2. And this is a 1s, 0, 1/2, 1/2. So this is not allowed. This is forbidden based on the Pauli Exclusion Principle. So we can't write that, but we can write this. Okay. And we get a spin down. Now this has 5 different, the 5 quantum numbers are distinct. 1s, 0, those are the same. 1/2, that's still the same. But then we have plus 1/2, minus 1/2. And so these are different states. And this would be the ground state for helium. Now, we don't want to have to draw this picture all the time. So we express this in what's called electron configuration notation. And how we would do that for helium is we would write helium colon, and this really is a product state. So we would go 1s squared. Usually you'll hear it referred to as 1s2 rather than 1s squared, but it really is a product state. So you're not wrong if you say squared. People might look at you a little funny because everybody's used to saying 1s2. Okay, well, let's go to lithium. That will add an electron here. We can keep adding electrons. Right, now we get up into the p's, and now we have to come to another rule. So we're using Aufbau to build up, Pauli Exclusion Principle to make sure no two electrons are in the same state. And now we use Hund's rule that says, if possible, the spins want to align, but this will never violate the Pauli Exclusion Principle. So this is an absolute principle here. So we can do that here. We can have another electron go here, and another electron go here. This is actually a lower state than, say, something like that, or something like that. The spins want to align. Now, we certainly could have, so this state and this state are degenerate. There's no difference here. They're spin aligned, but all downward. We tend to just out of habit, I guess, start with the spin up state. Now, finally, we get electrons coming in, and we can refill. And there we have a full P. We can't get any more in here. So then the next can come up here, and so on. Now, let's say we filled up all the way to here. By Aufbau principle, our next position is here. And then finally, we get to the D's. So we actually fill the 4s before we fill the 3D. And if you remember back to when we first talked about hydrogen, and we said that the solutions from the quantum mechanical calculation give us these states. We talked about the degeneracies, and we saw those degeneracy values matched the different elements across the rows of the periodic table. So we said the hints of the periodic table are already there with hydrogen. Well, now we can see by applying these principles exactly how the periodic table comes about. Down at the 1s, right, we have the case where we have one electron. That is hydrogen. Then the next electron. Now we have two, so that would be helium. Now we have to go up to the 2 case. And so, first of all, we get the S block, because we're filling the 2s first. The S block, 2 there, and then an additional 6 here, across here in the P block, as we go across. And there's our 8. Then, okay, why isn't it 18 next, but it's 8 still? Well, let's go back up here. We have the 3s. So now we're in row 3. 3s, here's our 2 of them, right here. Now we're going to go across and fill our 6, but we don't go to the D's yet. We wrap around and go to the 4s. So the 4s right here. And then finally, the D's come. So that's why in the structure of the periodic table is such that we go 2, 8, 8, then our 18 across here. And then that continues down. And then when we get finally filling up the F shells, then we start to enter the lanthanide and actinide elements. And they're written down here just to keep the table from getting so long, but they would be squeezed up in there as we build up to them. All right. Well, let's just come back to this electron configuration notation, and let's just use an example. Whoops, let me probably leave. Well, actually, let's just work with the periodic table. So the periodic table is a great tool for us now because it captures that alpha. We don't even have to draw the energy level diagram we had over here. So let's say we wanted to get silicon here. So here's carbon, here's silicon right here. So let's see if we can get the electron configuration for silicon. Si, right? We could draw this. We could draw the picture we had here and just build up very systematically until we run out of electrons. But let's just do it with the periodic table. So we just start sliding across. We get 1s2, right? Then we wrap around. We get 2s2. Then we get 2p6. Then we come up here, we get 3, I'll write it down here, 3s2, that's there, and then we go 3n, 3p3. And that's the electron configuration for silicon. Now, we can get even lazier than this and say that when we reach the noble gas side of the periodic table, we have a completely filled shell. And then everything, the electron configuration would be the same for any element past that by simply adding the remaining electrons. And this is called noble gas configuration notation. And so let's write silicon in noble gas configuration notation. So we come through here, we get helium. We've come through here, we get neon. Now we don't get all the way to argon. So we write this as a square bracket neon, meaning that's all of this. Right? This is neon. And then the remainder comes like that. And that's very handy, especially for the high level elements there. You can use the noble gas that you have just wrapped around and then add in the remaining electrons. So this is an example for silicon. All right, so I think now is the time for you to practice a bunch of these. Just choose different elements of the periodic table and try to write the electron configuration notation. Now what you'll notice, and take note of this when you're doing your practicing, there will be some that you get incorrect. So you can just try any element. Maybe find a periodic table that has the electron configurations printed on it, and then find a periodic table that doesn't. Choose any element at random and try to see if you can get it right. Make sure you're getting all of these right. Now, as you start to get down into here, some of the higher n values, what you're going to see is that you're going to not match with the right answer, but you still did things correctly based on what we've learned so far. So next time we'll pick up the important concept of spin pairing energy, which is related to Hund's rule, and that leads to exceptions in the electron filling. So that will be an important next step for us. We'll also look at something that isn't so much in general chemistry books, but I think it's a good way to practice and get this down, and that's term symbols, which comes out of the field of atomic spectroscopy, which is used a lot there and then maybe not so much anywhere else. So if you were to become an atomic spectroscopist, you would need to know that a lot. Not so much other areas of physical chemistry or science or chemistry, but still I think it's a really valuable just to get some of these concepts down. All right, so we'll do that next time.